In this lecture, we'll begin looking at architecture. And while I'm lumping architecture in with studio discipline, obviously it is an entirely different animal altogether. But because of the visual aspect of architecture and what architecture has to offer, it is often put in with the visual arts. So starting off, we're going to look at cliff dwellings in Mesa Verde, Colorado, part of one of the Pueblo societies. And architecture comes about, for a couple of reasons. One, obviously, to escape the elements, to get out of the wind, the rain, Colorado, the snow, to get all of that, stay nice, warm, and dry. The other aspect with the formation of society and civilization is defensive purposes. So here at Mesa Verde, they built this in the side of a cliff, so nice big recessed area where they built their multi-level apartments and the kivas, their little ceremony spaces. So the rock shelf overhangs to help sort of protect from the rain and snow and all of that. And being high up on the side of a cliff, if you wanted to attack this area, it would have been rather difficult. Another aspect that they took into consideration when building this is its location, or that it faces the southwest, so that basically during the daylight hours, it's absorbing all the heat from the sun, so that in the winter, where it really has a lot of the full exposure, it gets everything kind of nice and warm, and essentially lower your heating bill for the purpose of that. So that this is actually kind of a green architecture structure before green architecture was ever a thing. So the first construction method that we'll look at is post and lintel. And post and lintel is simply two columns, the posts, and then the lintel up top. The lintel sits on top of the posts. Pretty straightforward. And of course the roof is held up by the lintel. So this example is coming from the Greeks. Of course, many of the earlier civilizations and cultures and all that before the Greeks were using post and lintel. It's one of the oldest styles of architecture, and widely commonly used. Of course, the Greeks and even the Romans that copied a lot of the Greek stuff, they pushed things much further with this type. So some of the different types, pieces that make up post and lintel construction. So again, starting with the posts, the columns there, and they're made up of a capital, a shaft, and a base. And the lintel on top is the entablature, and you can see all of its different little parts. And then on top of the entablature, the lintel basically, is the pediment and the cornice, and that's basically the parts of the roof. So you can see how it all works. And the thing with post and lintel is, you're limited on how high you can start to build and how far apart before you start to reach a point where your lintel, there's not enough support and it comes crashing down. Your design gets compromised and you get into structural failure. So always a bad thing with architecture. And parts of the Greek columns they're known for their orders. So the Doric, Ionic, and Corinthian. So with Greek buildings, oftentimes you can kind of date them by the different columns that they have. So when Rome comes in and they start taking over things, they're already highly influenced by the Greeks to begin with, but they take the Greek order and they use it more of a classification system, so that the Doric columns are in the working class, Ionic, merchant class. Corinthian is strictly for the noble class. Sometimes the Ionic and Doric can kind of be changed around. If you have to build a new building and you want to keep the working class people happy, give them little fancier columns like the Ionic. That'll do the job. But the Corinthians was strictly for the noble class. That was never a part of being interchanged with the other ones. And so the next, the rounded arch. So here the interior of St. Foy. You can see the rounded arch, and the benefits of it when the arch comes into play is you can build higher and wider than you can with the post and lintel. It's also a little more secure, more stable type of structure. And you can see if you line a whole bunch of arches up, you get a tunnel or barrel vault. You take 2 barrel vaults, turn one perpendicular, and then you get what's referred to as the groin vault. So it has a lot of potential and a lot of uses that comes from the use of the arch. And along that lines, then we get the pointed arch. So instead of being rounded at the top, it comes to a point. So here inside of Rheims Cathedral in France, using the pointed arch, where you can kind of see it, the different bays up there, and going into the side aisle, all these pointed arches all over the place. And it's basically what helps give rise to the Gothic period, because you can start to build higher and wider than you can with the rounded arch. So that's where you have these, real strong vertical pulls in the Gothic churches, as well as some of the Islamic mosques, where the Islamic culture is basically responsible for the pointed arch that they introduce into Christian Europe. And of course, we'll get into that a little bit later on in the lectures. And so on the outside of these massive churches, some other kind of architectural terminologies and things to understand. As you build higher, you have to support the walls. So you have buttressing. So buttressing is basically like a little perpendicular wall that you would put up against an exterior wall, and it sort of helps to transfer the weight as well as supporting the wall. And the higher up you go, the bigger your buttresses need to be. But of course, if the buttresses are too big, then they don't allow any lights to go through. So what the architects basically come up with is a flying buttress, so that you move the buttressing away from the wall necessarily itself, and that of course creates what's called a pier. And from the pier basically are like arms that come out and hold up the wall. So it's basically, if you were to stand up away from a wall at about arm's length and then use your arm to help support the wall. And that's basically, what flying buttresses are. Buttressing would just be if you were to stand flat up against the wall and help support it. So the next is dome, and the dome is still, based on the arch. You just spin that arch 360 degrees and you get a dome. And so here the Taj Mahal was built by the Islamic culture of the Mughals. And this particular type of dome is often referred to as an onion-shaped dome. So inside the dome, there's these massive piers or columns that are supporting all of it, and the pendentives are almost like little, almost like quarter domes that support the bigger dome. So domes really become one of the ultimate types of structural engineering. As with the building of Hagia Sophia, as you can see the cross section, you have the one massive main dome, and then as you kind of move away, you have these smaller half domes that they're all there to support the central dome. It's basically what happens is it transfers the weight, from the roof away from the main four piers. It carries out that weight all throughout the building. Of course, as you start to build things higher, you also have to think about, not only the weight of the building, but the force of the wind, pushing on these buildings. So you really have to find ways to strengthen them further, like we were just looking at with the Gothic cathedrals with the buttressing and the flying buttresses. So with the Hagia Sophia, again, it's just like dome after dome after dome, they're all supporting each other. And then this example, the Pantheon in Rome. So for the longest time, the Pantheon, built in 118 to 125 CE, Common Era, for about 1700 years, it was the largest unobstructed enclosed space in the world. So it's basically like roughly 128 feet across. So if you get like, a 128 foot beach ball inside this thing. And on the outside view, you can see it's these massive, massive, thick walls. If you were to, look at a close-up of the walls, the walls are actually built in with arches on it. Again, it's to just help to shed the weight, help transfer all that weight, shed the weight off the roof, through the walls, down into the foundation. And then on the inside, that sort of decorative detail, that actually becomes beneficial because it's like removing weight. So the engineers figured out, okay, if we have this kind of design, we can remove material, making it lighter, but at the same time, it also strengthens it by the pattern that they create. Whereas again, going back to the exterior view, you can see where it stair steps on the top. So that's, removing a little bit of material as it goes up, and the opening, the opulus, that of course is there to add, even more strength. Had they closed it in, then that would actually be the weak part of the dome. So by taking it away, it actually adds strength. And the other kind of mind-boggling thing about the roof of the Pantheon is it's one single piece of cast concrete. So it's just one gigantic piece up there. It's not a bunch of little segments put together. So the next is balloon frame construction, probably what we're a little more used to seeing today. Most of the houses, apartments, things like that, it's made with balloon frame construction. Of course, some where the materials might change, but essentially it's the same idea that you have this sort of internal support system. So like it says, a skeleton and skin method, so that you have the wood framework in there is, that's like the skeleton, and the skin, the sheetrock on the inside, and the brick or wood siding, whatever you put on the outside, that also helps to create a little more stability and to hold everything in place. So it all kind of works together, and you're getting into the self-supporting systems. So an example of, balloon frame construction, like I said, we're all pretty much used to it. We all probably live in something, that's a balloon frame. The next, cast iron. So cast iron comes about because of the Industrial Revolution, where you get better, cheaper material to build with. And getting away from stone, because stone has its limitations. With cast iron, again, you start to get in this self-supporting type system, and also it gets into prefabrication, so that as stuff is leaving the foundries and the mills, uh, for the Eiffel Tower, by the time it reaches Paris, it's ready to be assembled. So that you're getting into, like I said, the prefabrication, where these pieces can be prefabricated, then sent to the site for easily assemblage, so that it goes up quicker and, again, cheaper, so that you're bringing the cost down. So the Crystal Palace, that was in London, one of the first massive kind of buildings using the cast iron. That's an enclosed space. Ironically, it burnt down. The next, steel frame construction, so lighter than cast iron, but kind of the same thing. Uh, where we're getting into these self-supporting systems, so that all the support is internal. So anything on the outside of this building is just superficial. So you can start, put whatever you want on the outside. It doesn't really matter. It has no bearing on the structure. So such as the Louis Sullivan Wainwright building in St. Louis, built in 1890 to 91, one of the first skyscrapers at like a whopping 13 stories. And so because of the internal structure system, everything on the outside is superficial, and you can get more decorative. It does not have any type of bearing on the structure. And then 1952, Gordon Burnshaft's Lever House. It's part of the international style that we're probably a little more familiar with, where you just have the nice, sleek, clean lines in the buildings. It's very kind of geometric, the big, massive floor-to-ceiling windows type look. So again, you can put whatever you want on the outside of these buildings, and it's not going to affect it whatsoever. And getting into reinforced concrete. So I'm sure we've all seen where workers are putting in like a new sidewalk or a new section of road, where they have all the metal bars and metal rebarb, or just almost looks kind of like a steel fencing or something that they're putting down. Then they put the concrete on top of that, so that it adds some internal support to the concrete. Again, you start getting lighter lighter structures, things like that. Reinforced concrete, you can also you can do a lot more with it than you can with the regular concrete. So such as Frank Lloyd Wright's Kaufman House, Bear Run, Pennsylvania, also known as Falling Waters. When the Kaufman family bought the property, the reason they bought it was because of the little creek that ran through there and all the waterfalls. And all the early architects were like, it's a great, beautiful property, but we'll be building your house up here by the road. Frank Lloyd Wright came along. And he's like, okay, where do you want your house? And they, so well, we were hoping to get it down here with the water. And he's like, okay, well, that's where I'm going to build it. So that's almost like if you're down kind of the basement levels, you're looking out the window, there's the creek right there running up against the house. And also when you're standing up on the cantilevered porch, how these porches just kind of stick out almost without any type of support underneath them. You're standing out above the little creek, looking down. So it's the whole idea that he wanted to put the family more into the natural setting. And steel cable architecture, typically, suspension bridges, so like the Brooklyn Bridge or Golden Gate Bridge in New York, Golden Gate Bridge in San Francisco, Brooklyn Bridge in New York. Basically, you have the two massive piers with the cables running across the span, and then they, of course, hold up the roadway underneath. And the fun part about steel cable bridges, that certain ones, if you feel like you're kind of moving around, is because they're basically designed to sway in the wind so that they kind of um, work with the environment. Then geodesic domes, basically Buckminster Fuller came up with the idea of the geodesic domes, and it's all basically based on the use of the triangle. You kind of look at the structure there. It's all a bunch of triangles kind of put together in different ways, different positions, and again, it becomes this massive self-supporting system. So that you have this nice, large, unobstructed area on the inside. This real stable type of construction method. And again, like the steel frame and the cast iron, you can kind of put whatever you want on the outside. It really has no bearing on the structure itself. Again, it's all this internal support system. And then more recently, as computers are coming in and taking over everything, using CAD design, so that architects can now start to examine to see if there's going to be problems in their designs, now getting away from trial and error so that they can, how is this design going to work, with high winds, or how is it going to help shed rain, so that the architects and engineers can, troubleshoot all this stuff using computers. Whereas before is kind of you build it and you hope for the best. Now they're able to, use computers, run simulations, test their designs to make sure it's going to work. And then finally, green architecture. So using uh, renewable material, reusing materials, using materials that You can see here they allow more light to pass through, so you're cutting down on your electric bill. Also they, trap heat. Others where they shed water, and that runoff water is used for, irrigating trees or using part of the cooling system. So that basically, more and more ways to reduce the carbon footprint. So that is it for architecture.